Jnanam paramam dhyayam. Knowledge is supreme.
Okay, so easy to see some first easy remarks. So suppose I have a module M, this is a graded module, and suppose I have integer k. From this module I want to get a new module, that I want to write it M k. This is a twist. So that means to define this graded module I have to give you what are its homogeneous components. So homogeneous components of this, if I write n here, that is by definition M k plus n. So I have shifted this only, if this module was like this, M minus 1 direct sum M 0 direct sum M 2, and if I have k is 4, then this component or the new components will be now I shift to this side. So that will be new mk will be, so k plus n, so this will become minus 3 mk, only the position is changing, right. This only you just shifted, so I do not write that, it is unnecessary to think about it. So it is just positioning. Okay, so the obvious question is, what is the relation between the Poincare series here and Poincare series there? So obviously the Poincare series of mk, this is z power minus k pm. This is obvious. You just have to shift the dimension to the other side, left side. Okay. And also, so this is, I am collecting easy properties of this Poincare series. So suppose we have, now before I state the next one, suppose I have two graded module M and N, graded module, R modules. Then what is the homomorphism between them? That should respect the gradation, that means homogeneous component of degree n should go inside homogeneous component of degree n. So it is called, F is called graded homomorphism. If f of mm is contained in n times m, then you call it graded homomorphism of degree 0 is called graded homomorphism. If you want degree k, then it need not go in but it should go in m plus k. So graded of degree k means not this, but this should go in, this is for all m plus k for all m, and if I do not say degree, then that is assumed that degree 0. So now suppose I have a sequence like this, graded modules, and I will also assume m finitely generated graded R module. That means as a module it is finitely generated over R, and because it is graded, then I can assume that there is a generating set consisting of homogeneous elements of whatever degree. So now if I have a sequence like this 0, now I cannot put a suffix here because I want a modules to be numbered, so I will write it here. So this is a graded module, another graded module, and this is a graded homomorphism, and so on. And do you know when do you say sequence is exact? So this is a long sequence of graded modules of graded homomorphisms, and we say it is exact, means so exact means image here equal to kernel here, and at this stage it is injective, at this stage it is surjective. If such a sequence of graded module is exact, then at each homogeneous stage it will also be exact, because we know it is a graded homomorphism. So this will mean that this mth component here will go to mth component here, and so on. So then this sequence will also exact for all m. So if this is exact sequence of graded R modules, then this sequence is an exact sequence of finite dimensional vector spaces, finite dimensional K vector spaces. But then when you have an exact sequence of vector spaces, then you can compute the dimension, and a alternating sum of the dimensions is 0. So that means, so then summation is from 0 I equal to 0 to R, alternating sum dimension over K as mi m, this is 0 for all m in Z. But this means what? This precisely means that, so this means if I take this series, Poincare series, summation, alternating sum of P m0, P mi, these are all 0, because Pm is by definition this. So all these coefficients will add up alternating sum to 0, that means as a power series it is 0. So let us see a concrete example of such a situation. So example, so let's we have this graded ring with our usual assumptions, it is standard graded, and suppose F is an homogeneous element of degree m, this is an Suppose f is homogeneous of degree m, homogeneous of degree m which is strictly positive, and suppose f is a non-zero divisor. In R, and let us, this means non-zero divisor means your map is multiplication by f is injective, this is injective, this is multiplication by f, this map is A going to FA. Non-zero divisor means this map is injective, but this is not a graded homomorphism. So, if I want to get a vector spaces out of this, I should put the correct indices. So, this means this I should think instead of Rn will go where, if I multiply by f, it will go to R m plus n. So, if I take homogeneous element of degree n and multiply by f, I get homogeneous of degree m plus n. And then if I still want to write this R here, then I better shift this to the other side, then it will become homogeneous. So, if I still want to think this lambda f as a graded homomorphism of graded modules, then to put the correct degrees, I should shift this R to the left side, so that it becomes homogeneous of degree 0. So, then that means I have to consider R and minus m to R. So, minus m, the homogeneous components are shifted to the minus side, so that is left side. So, if I have homogeneous of degree some element here, then now this becomes correct, this is a graded homomorphism. And then what is the co-kernel? So, this is injective. So, I have injective homomorphism, and what will be the co-kernel? Co-kernel is R modulo ideal generated by f, and this is, I do not have to do anything here because this is homogeneous. This is also have a grading already because it is a quotient of a graded. So, here you can put, this is same thing as Rn mod, this has the same grading, Rn mod Rn intersection with this. So, this already, so this I have an exact sequence of graded modules, and just now what we have seen that the Poincare series here alternating sum is 0. So, that means the middle one, so the PR is equal to P of this plus P of R by F, because alternating sum is you start with, if you start with plus here, plus minus plus. So, this minus I am shifting it to the other side. So, it is PR equal to the P of both these, and this one again just now we have seen that this is, that power will come out. So, this is same as z power m PR plus P R by F. So, and there is nothing special about the ring, I could have done this for a module, and only thing I need to assume that this homogeneous element f of R should be a non-zero divisor for the module M. So, let me write now the statement. Let us simplify this little bit. So, we should write this in terms of the other PR. So, P R by ideal generated by F, this is same thing as I am shifting this to the other side, this to the other side, that means 1 minus z power m PR. So, if you want to compute the Poincare series modulo f, then we have this inductive formula, right. So let us write in the form of lemma now. So, this is lemma which will be used again and again for computational purpose. So, I will write more precisely. So, let m be a finite graded R module. R is n graded of finite type over a field K with that R naught is positive dimensional, and of course finite, and if and f is R m homogeneous element of degree m which is a non-zero divisor for the module, for the R module m, then Poincare series of m mod fm. Note that f times m is a graded submodule of m, and therefore m by fm is also graded. The graded homogeneous components are precisely the homogeneous components of m divided by the homogeneous components of f times m. So, this equal to 1 minus z power m times the Poincare series of m. Now, proof is same. Proof, you just have to look at the exact sequence 0, m minus m, m to m by fm to 0. This map is a multiplication by f. Any element x goes to f times x, and this is a natural map. So, this sequence is the exact sequence of, is a short exact sequence of graded R modules, and therefore, you write down the Poincare series, and whatever we did, the same calculation shows it is this. Okay, now I will state a theorem and we will continue the proof next time. So, this theorem is very fundamental theorem, and this was already actually proved by Hilbert. But Hilbert had a very complicated proof of this, the theorem I am going to state. So, theorem, and again if one states very precisely, that it will be clear what to do in the proof. So, R and M as above. That means R is a n graded ring with R naught algebra over a field which is finite algebra, that means finite dimensional K vector space, and R as a R naught algebra generated by finitely many elements. They may not be of degree 1, they may be different degrees. Then, so let me just to remember write this R as R0 generated by x1 to xn, and this x1 xi degree of xi or xi belong to R gamma I is from 1 to n. That means R as R naught algebra generated by x1 to xn, which are homogeneous elements of degree gamma 1, gamma 2, gamma n. Okay, then the Poincare series of M, Pm is same as some Laurent polynomial Q divided by, it is a rational function of the type, the numerator is not just a polynomial, it is a Laurent polynomial Q, and then denominator is Z gamma 1 minus Z gamma n, where Q is a Laurent polynomial. Q also depends on M actually, so I should really write here M. Qm is Qm belongs to integer coefficients and Laurent polynomial. So, Z power plus minus 1. So, Laurent polynomial. With integer coefficients. And the denominator is nice. So, in particular, when, for example, when you want to do it for R, then it will be and suppose your polynomial ring, then all gammas are 1. So, you can, so it will be 1 minus Z power somebody if all gammas were 1. So, we will prove this next time and deduce consequences from here. So, proof next time.